Okay, so I'm having the Bezier curve here. Going to drag these things around. The Bezier curve goes through P0 and P1, and they start in this direction and then arrive in this direction. The curve is red when it's the opposite direction, in which case there is no Bezier curve that enters from this side. You have to pick one where it is black. It's here. And it goes through P comma, where the curve is then adjusted such that the gamma or G were at which point, well, if at t equals G, the curve goes through P comma. Then we pick that G such that the curvature is minimum. And you see here what the value of J is. So the jolt. And it is a minimum here at 0.2 something, 0.24-ish. Yeah, and the G that is found was 0.248. It's almost halfway, I guess. So that works. But of course we are finding this minimum by taking the derivative of this thing and then see where it goes through 0. It's horizontal in the minimum. So this should also be the point where the derivative of this thing goes through 0. In fact, the square of this thing, the derivative of the square of this thing, which is, well, then you avoid the square root. So let's try to draw that. Well, it is calculated in this function. Let's see. This stands for the norm of p prime squared, and then the derivative of that. So this is well, prime is not the derivative. It just means that it is scaled with some constant factor. But if you minimize that, then you also have the minimum, of course, of J itself. And the norm is the length, and the square is because I don't want to take the square root. But if you minimize the square of something, then you also find the minimum of the square root of that. In other words, at the moment that this goes through 0, we have the minimum. So I'm going to draw this. But yeah, it's a local variable. So how to... No, it was a local variable. And now I made it a member of this class. So we need an accessor to cubic Bezier curve. Let's see, this looks like it is a member of... it is still a local variable of the Newton-Raphson function. I'm still hesitant a bit to move that around. It's also on the stack. I'm really thinking in assembly here to think if it is slower or not. I mean, this is being called from, let's say, in the fast path from here in the while loop. And that means that hopefully this is inlined. It should be inlined. But tell the compiler to always inline it. Fact. I would think that this should be calling. Yeah, we have to make all variables part of the object. Then instead of them being on the stack in this call, which we repeatedly call, it's already on the stack of the caller. Here. That would probably even be faster. No longer be const. Just make them double. JG return, and then they're all assigned. So I guess space equals anything can be replaced with a semicolon. And then we don't need comments. Maybe I should keep them actually, the comments. Delete print, delete print, delete print, delete print, delete print. join, 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 join. And then let's clean up a little bit. Substitute, yeah, let's say semicolons at the end of the line can be gone, as well as dots. And then a semicolon followed by I'll make it better, I think. Oops. Right, so now everything is here and I should be able to just access it. Get the derivative. But we need these things to be a function of g. Means I need to change g and then call initialize. Which is not true. I need to do one loop of the Newton-Raphson now to get these things initialized. Initialize is just using the g to define the return vector, I think. It's basically a const. Recalculates h, and then the rest is just local until we get the answer. Oh, the m is changed. It initializes the Bezier curve itself and then returns a vector. Oh wait, this is not Newton-Raphson here, it's just a single step of Newton-Raphson, so that would be good enough. We can change G and then call Newton-Raphson once. We just initialize everything for that given G value. And then in the end it also adjusts G. Return true or false, but yeah, we don't really care about that, I guess. Okay, still have to change all of these things. So just remove the double constraints. Just going to split this up. Feeling I should not make G part of the object though. I guess everything still works. Let's remove the G from here. These things are not public, so that's a red flag, isn't it? Yeah, and then this function has to go. We can just incorporate it in the other one that is calling it. So then H is already known now. Can make that an assert though. It's totally broken, but I'm gonna fix it in a second. Okay, we have to call this, and then I have the derivative, so we can calculate the delta G using the Newton-Raphson method, aka divide one derivative by the other. And then if that step is, well, that step is still larger than 1/1000th of what we are trying to change here, repeat that. So at some point the delta G must become 0-ish. This is no longer true. And then we calculate the rest, the Bezier curve. And the initialize is, yep, that is returning this this S here. So. But it looks of it, we also don't need delta G actually. It's part of. Yeah, we don't have a G anymore, so this does not exist. It's a bit heuristic anyway. I want to get rid of these things. Now I have everything. Delta G only exists in this function. And so should G. What the heck? Komt ie, joh. Oh boy. assertion fields. Well, okay, so apparently I didn't do this, and I'm a bit confused here though. Yeah, it's needed for h, but it's not really needed for the rest. I think I only need h and g. I don't need derivatives. So maybe this doesn't hold for this call here, cubic from. Yeah, these are adjusted one more time. Yeah. Getting it. How to solve that? I guess it's just not true then. The assert is wrong. You can call this with any g you want. I just have to recalculate h. The cons doesn't change the assembly code, but sometimes it's easier to read if you know in advance that it is just a one-time calculation. So especially with very complex code, I just I like to add a constant. I know, here just calculate this, and then we have it. It's not going to be changed still at all. That's what it tells me. Let's see. Yeah, this should work. No, it still works. Hello. Isa says, how long do you write this code? I've been coding C++ for 30 years. And this code, the last character was typed a minute ago. And the first character of this file yesterday. Oh wait, this is Bezier Curve. Now, I'm working on Cairo window for half a year now, I think. Machine learning longer. I'm always working on sub-problems of sub-problems of sub-problems, and they all have their own time scale. So this, the title of the YouTube, Improving Drawing a Function Using Piecewise Bezier Curves, is kind of a week now, I think. Maybe even less. Okay, and then in the meantime, I kind of got what I was doing. So I have, it works, right? But I need access to the derivatives to draw it. And that is now part of, that is this derivative function, for which I need access to a curve implementation, which is totally hidden in this file. We have an impl here. So you can call initialize from G on this one, and then get the derivative from this one. Maybe it's stupid to do that like that. I mean, let's just keep it on one line. So then I need this object, call initialize from. Oh, wait a minute, I only have, the user only has this, so also this must be a Wordle function then. No, yeah, let's make even that one. So they're all Wordle functions. So we need these two to be Wordle functions of the cubic Bezier class thing. Really work. copy this, and then we jump here. Oh, great. What? Oh, C-text only jumps to the initial the definitions, not a declaration. But that's going to be part of this. There it is. Virtual. So now we can call it from here, provided I have a cubic Bezier curve thing. I should get that by calling create. So somewhere we are calling create. That gives us an object which now has the virtual functions. That is what we need. I'm already calling this, I have the feeling, so might as well now write this and then grab for that. Yep, that's our current test. So now we can not, I'm just not calling J now, I'm going to call the derivative. Derivative. Nobody knows what the value is of that. We just have to plot it and see if it is too small or too large. It's definitely going to 0, so we should be able to see it. Or not. Empty window. Damn it. Nope, nothing. One possibility is that it is just a horizontal line here on around 0. So the values are way smaller than 10,000. Let's print the values. So we know how large they are. A lot of derivative. That's the one I wanted. Rotation derivative. Yeah. I don't know. Let's just print it. Zero. Doesn't make any sense. Hey, Koto. I mean, we need a derivative to calculate the delta G. And it's calculated here and there, zooming in on the correct G. So it starts at a half, and then we go there, and then it hardly changes anymore, so we stop. In the meantime, it should have calculated the derivative, but it's not printing it. Why not? It must be something stupid, Kotaro. I'm sure of it. I just waited for my subconscious to come up with a solution, but nothing came. Totally calling derivative here. It's totally weird. So this is being printed, which can only be done after calculating it, which is done by calling derivative. And that is not printing anything. Why? Oh. Oh, just calling this one. No, but that is calling implementation. It's a function still. This should be calling that. Well, no, I don't get it. So time for the debugger, I guess. Let's put a breakpoint at where this is printed. So here, or just here. Now, I'm not even worried about the value of 0 at the moment. I just don't get it why this is not being printed in between here. Oh, it is. It's it is being printed. Okay, never mind. Yep, I was completely not seeing that it was being called. It is called. Okay. Well, in that case, yes, we are now interested in why this returns 0. Probably missing an initialization function. Yeah. Another. Oh, yeah. It's just drawing this piecewise Bezier. So if everything returns 0, then it just calls it a few times. Only 8 times or 7 times. 7 times, yeah. 7 times to get a single Chebyshev polynomial thingy, which uses 7 points, I think. And because everything is 0, it just says, well, probably it's going to be 0 in between as well. Something like that. So the only and main problem is that it returns 0 in the first place. Well, that should be happening here. Initialize from G. Called on. That is a virtual function. So we should end up here, which then calls initialize on the implementation. Oh. Okay. Yeah, never mind. This is not, that's not what you want. It just initializes the Bezier curve, but not the not this. You have to calculate the derivatives. Yeah, so just some missing initialization. Maybe move that into this as well. This whole thing is debug anyway. Let's see. Is this a virtual function? Jesus, not that again. Yeah, this is a. Let's just pass G to these. It's just debug stuff anyway. Okay, I lost or where I was. Damn it. Hopefully here. Nope. I just want to pass the G here. Then the Bezier curve itself is not initialized because we don't call this. Maybe we should call that too. No, I'm just getting the derivative, so I don't need to call that one. It's no longer constant. Unless I make all these things mutable. Let's not do that. Yeah, or I can have the virtual function as successor and then a single function to calculate the derivatives. Nah. No, it's calculating stuff. And you get a vertical line. Great. So the thing goes to very, very high values. Man, I probably should just draw the logarithm of this. I can't take the logarithm of a negative value. Well, let's start with 10 million. That should give something. Something more sensible. Oh yeah, and then of course minus 10 million to plus 10 million. So here is the derivative. We want to minimize that. Well, we want to find a zeroid, which is just there. And we totally succeeded in that. But what if we pick something else? There's something goes wrong here. Totally, like, well, the disappearance is concerning. It's not being drawn here. And I think I already see the reason. Yeah, I can guess it, right? We start at a half, so if you take the derivative of the derivative here, you draw a straight line, that's going to... No, wait a minute, that's not true. So Newton-Raphson would work like, you find this point, draw a straight line, and then that hits x-axis there. Then we go down, draw a straight line again, and that should hit it like there, and then there, and then there, and then we find it. But what really happens... We start with the g as a half, and well, actually, indeed, it goes to 0.6. So in a half, draw a straight line, hits in 0.61. So that would be somewhere here. So that kind of seems correct. Then we enter that one, and then it hits in 0.77. So yeah, so nothing wrong there. And then we repeat it, and we should get closer and closer and closer to this 0.9 value. But apparently not, because dang, here it goes wrong. It becomes larger than 1, and I think that is why it totally goes wrong, because yeah, the derivative of this function is not going to help anymore once we are larger than 1. It probably still has a value though, so maybe I should draw this for a larger domain, let's say from -1 to +2, see what happens. I'm gonna blow it up a factor of 10, because it's definitely going wrong here somewhere. And let's draw this from, well, 0 is good enough. In fact, 0.5 is good enough. And let's go to, I don't know, 2.0. And then it can't plot it at the value of 1, because then it goes to infinity. But hopefully it's not going to crash or doing weird things. It's totally not what I expected. Oh shit, my curve is back to what it was. I need a way to store everything that is draggable, I think. I ran into this so often. It's quite some work, but in the end I think it might pay off. So I can drag this around, and then drag this, and drag this, And it would be nice if I just remembered that. So the next run, it just starts at the same place. Everything. Okay, but at least now I see what is going wrong, right? So if you draw a line here, horizontal line, then that totally hits the curve there, larger than 1, while we are looking for this point. Newton-Raphson is majorly failing here, majorly failing, because the function doesn't even exist here. Yep, okay. So the problem is that Newton-Raphson doesn't work on this function. Surprising, but true. In fact, it does work as long as this derivative cuts definitely before 1, of course. But if you do this, it starts to look like something like close can I get? I think it bends back even. It's going down even here. And then suddenly, boom. How to find that 0? Nope. And any value outside of the range 0 to 1 is just nonsense. Just can even abort earlier. So if we even get out of the range once, I currently stop, but we need to do something else then. Switch to a different algorithm. Just want to do some investigation on the general shape of this thing first. Normally it just looks like, what is this, an arc changes or something. It's like totally monotonically going up. It's only when the value comes near 1 that did you get this weird kink here. And surely it will be possible to do that on the other side as well. Okay, so this is, yeah. Oh, wow. What a horrible function this is. Yeah. Oh, beautiful. Beautiful. Wow, look at this. It's going to be extremely hard to find this 0 here. It's like a vertical line here now. Yep, I think that this blow up is a result of dividing by the I think even g, well in this case 1 minus g to the power 4 or something like that. And then, of course, if we move it to the other side, you get the same thing here. So it must be symmetrical, yeah. Because you also divide by g to the power 4. think about how long it will take me to add this option that I can save the draggables to disk and then load them again. It's yet another distraction. That exists of several difficulties. I have to add a button, or I could make that a key. And then we have to serialize it. All the draggables, which I probably already have in the list somewhere. And then of course read it in again. I'm very bad at guessing this. So usually I think, well, let's do this. It's going to take me less than a day, which is also what I think now. And then that's going to take a week, apparently. So I don't want to put a week into it, really, because the only reason I would do it is to gain time. I don't have to drag it to this position every time I start a program. So far what I did is just print the values and then hard code them in. If I can get this back. I think these values, right? Not everything. So the directions and all the points, yeah, this is all. So for now I suppose I'll just copy that again instead of putting a day or a week into that. Here's a later version. Yeah, that's definitely the fastest way at the moment. But yeah, eventually I'm going to write it, I have the feeling, because I run into this so often. And then it's usually, why not now? Because in the end, I'll write it anyway. So the sooner I write it, the more I will benefit from it. And then how do I translate my t values? No, I'm not even using Q. Those I have to convert them to a file. Let's create let's just make 2 direction vectors. It's not really, do I have a T0 at all? Yeah. No, that worked. Hello, Daniel. My software. I don't know what exactly you're referring to, of course. If you refer to the code, yeah, I wrote it. Now I see this works. It just reproduces the end situation, including the function. I think I can remove this. It flutes my debug output a lot. Hello, Aaron. So we have to figure out a method to find this 0 here. This is not really interesting anymore. You have this function, and it's a shitty function, which is definitely not working for Newton-Raphson. So currently, you find the slope in this point at the half, and then we draw a line that crosses the 0 like here, and do that again, which crosses it, I don't know, here. And then it's negative. I would say we go back to where are here or something, maybe back. And then forward again, and then, I don't know. yeah, if we start at this point and then we draw a line, then we go below 0, where the function doesn't even exist. What to do if that happens? In that case, you know that we are in a situation like this, and it's probably close to 0, but still before 0. I think a good gamble would be to maybe go halfway. The only problem with halfway is that if I end up here and we want to go backwards, that's definitely not. I never want to go backwards, because going backwards would be trying to find this minimum here, which might or might not cross 0, but I know it doesn't. So going backwards is as much bullshit as ending up below 0. So I think that as soon as this happens, we just want to halve the distance to 0 until Newton-Raphson works again. So I think what I should do is, if we go past 0 or if we go backwards, then I should switch to a different algorithm, or instead, I think this also has a name, bracket algorithm or something like that. So we're here and we know that must be between 0 and where we are. So we just go halfway. Now we go backwards, so we go halfway again. Now we go still backwards, so we go halfway again. And then we are going backwards, but with a reason, because the function changed sign. So now backwards is okay, and then we can use the Newton-Raphson again. And then this should almost immediately find this point. Hello, Bambunium. So then the definition of backwards means that the sign of the second derivative is different from the sign of the current derivative. Yeah, I don't know. It is the case in this case, right? I mean, the first derivative is positive here. So whenever the slope is negative, so the slope is the second derivative. Negative means then if we go down, then the second derivative is negative. So if the sign of that is different from the current sign, then we go the wrong way. But if you mirror this on that side, I can probably just move this point over here. Yeah, now the first derivative is negative, and going backwards means that the slope is negative. So here it's the other way around. So we can throw in something else, like g minus a half. Because in this case we're on this side, and in the other case we are on this side of a half. And if you are in the neighbor of a half, that is, if it crosses 0 in the neighbor of a half, well, let me find that point. Yeah, that is just such a smooth function. We'll never have. Wait a minute, actually. So it would change sign then here, right? Wait a minute. No, but it's also exactly where the other thing changes sign, the derivative itself. So in this case, the second derivative is always positive. doesn't really matter if you're on this side or on that side. But the first derivative is the thing that is being drawn, is now negative on the left of the zero. Of course, like trivially so. Positive when it is positive. Okay, I'm confused. If you look at the sign, okay, so the sign of the first derivative is negative here. And the second derivative is positive, so the signs are different. And because of the signs are different, we have to go to the right. And here the signs are equal, therefore we have to go to the left in order to get to the zero here. So whether we must go to the right if, of course, we are on the left of the zero, and we must go to the left if we are on the right of the zero. And then the reason is that exactly at that point the sign of the first derivative changes, while the second derivative doesn't change. And it just holds and holds and holds and holds and holds and holds. It holds until we curve backwards, like this. So something is wrong at this point. This is still making sense, but here, now in the region between this maximum and this minimum, we have a problem because the sign of the second derivative changed in between here, while we still want to go to that direction. And Hawk token. This is the derivative of, well, it's printed wrong. It's a derivative of the length squared of j. So the square of the length of j. But then the derivative of that. So really it's the derivative of, I'll type derivative. But yeah, what I typed is the actual derivative, so the derivative of the square of the length of j, not what's printed here. So I'll fix it. And then yeah, root finding. So I want to find this 0 here. I also have the second derivative, so the derivative of this function. Can draw that as well, but maybe it will have different values again. Well, we can just draw it and then scale it maybe. Let me do that. Where is my test function? Cubic 2. Derivative. Yeah. I need a new Bezier pattern. Suppose I don't have to do this again. That's a bit big. So I think I should scale it down. Well, that's still usable this, but still, scale down would be probably better. So this red thing is the second derivative now, which is the derivative of the purple thing here. So at the moment that the red thing is going through 0, then this one is horizontal. So it's horizontal at this point here. I'm trying to think of a way to detect reliably, considering all the possible shapes that these functions can have, that we're going in the wrong way. That is, detect that we are in between this point and that point, if it exists at all. Now in this case it exists because you can see it, but if I move this point a little bit to yeah, let's say this now, the red thing is positive all the way, so there is no minimum maximum here where you can sit in between. So in this case, it should never happen that we detect that we go in the wrong way. And the reason is that the red thing is just non-stop positive. But if we go to the other side, so here, it's also positive. Oh, no, that's easy. It's just always positive. So if the thing, yeah, let's just divide the thing by 10 because it's clearly usually too big. Well, not going to change the y. Sorry, I want to change. I have to scale this here. Second. Not in the same graph, so. Puts both windows on the same spot. This is because they can't see the difference between them, I suppose. I need to give one of them a different window class, I think. Nah, doesn't matter. Yeah, so as soon as the second derivative is negative, we have this problem. Very simple. Between this in this range, you have to ignore that value. So here it's always positive, 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 positive. Just as long as it's positive, there's no problem. We also draw it, as you can see. Then the curve is being drawn, which means that there's no problem. And now here, the problem starts to occur exactly at this point because it disappears. And that is actually happening before it becomes negative, but that's the other detection. Now, if we say we are here and draw a horizontal line, when you get beyond 1, so the G value becomes larger than 1, which is kind of nonsensical, of course. It's pretty awesome, this. Say so myself. It's also pretty fast. I mean, I'm dragging a point and then just doing a lot of mathematical calculations and still able to draw 2 graphs with that. Okay, anyway, I'm forming a solution in my mind. If the second derivative is negative or we get out of bounds, then we want to switch to a different algorithm. Not Newton-Raphson, but a bracket thingy. No, let's implement that, I guess. Yeah, must be easy actually. That is easy. No, this is from cubic from. So we can calculate delta G, but then subtracting that would be Newton-Raphson. And I have to check the sign of the second derivative, so no, I have to make that a separate thingy. See, when is delta G not normal? The second derivative is 0. So that should probably never happen. Could also be not normal, it's also infinity. You can get infinity here when the derivative is close to the maximum value, so 10 to the power 304-ish. And then divided by something with a negative exponent. This is not going to happen. But if it happens, but it's not going to happen. I think the only problem here is that this is possibly 0, and we already took care of that. Well, let me think about it. If delta G becomes infinity, yeah, then we go just simply outside the range of 0 to 1 as well. Kind of. So the is normal, it just no longer has to be checked. I can just use this. Yeah, now I have to detect a boundary, aka 0 or 1. Yeah, I think that G is already near the boundary, so I can just compare it to the half. And then this test, yeah, I guess it still holds. So maybe I should instead work with, not with delta G, but with nu G. Thus, use bracket algorithm. Closest boundary, G. Yep. Now this never going to happen anymore, right? Mhm. Did it find it or did it not find it? It's kind of in the way now, isn't it? New G, 0.996. No. It's in the neighborhood of 0. What the F is happening here? Well, this is bullshit. It should go the other way. At a half, the red thingy is positive, which means you go up. And we have to go to this side. I mean, we just want to go to the 0. So I have to subtract it. I have to subtract what? Both are positive. So I have to subtract this one divided by that one. Or the other way around. Anyway, it's positive, so we have to subtract it. And that gives us it should have given us 0.3 something. Instead, it's going up. I don't get this at all. Yeah, so it's subtracted and I'm adding it. Guess it was a thingo. UG 0.01. Is that 0.01? I guess it is. So eventually it did use because this is only printed when Newton-Raphson is used. Eventually it uses Newton-Raphson. And this is the first time it would have used the bracket because it's a negative. Let me just print it. No, that seems to be pretty working. So you use Newton-Raphson until it fails. And then we switch to bracket, which is half it and half it and half it and half it, until we get close enough to be able to use Newton-Raphson again, which then zooms in. in 4 steps is good enough. Cool. And that leads to this curve, the red one. Yeah, cool. So before it could not calculate it when I was close to one of these points and then crossed the quadratic Bezier. Now note that the quadratic Bezier, which is this one, it has j set to 0, obviously. I mean, that's why it's quadratic. The third power of t is has a coefficient of 0, which is j. So this thing does have, well, it does have a curvature, right? It's a jolt. This thing has the same curvature everywhere? No, also not. I don't know. The j is 0. Let's put it that way. So if I put this point, and this curve is minimizing a j. So if I put p gamma on top of the quadratic one, it should use the quadratic one, because that then the minimum j is equal to 0, obviously. See, so as soon as you put it on top of it, it's just going to be equal to that thing. And it can only do that by finding this minimum here. Which now perfectly seems to work. Cool. So turn this thing the other way around. Now you could argue that if you are this close, then you have something that is numerically unstable. Starts to be. No, if you look at this graph, it's not even that bad. But yeah, you demand a lot of the precision of all the inputs. If it is this close, I mean, of course, you cannot say, oh, it has to go through P0, P1, and P gamma, which is here. You cannot say that then you know that it's going through this point. This is bullshit. Just these two are too close. But hey, we have a backup plan for that. This is just the first step. It seems to totally work. These are the control points of the Bezier curve, by the way. Yeah, what's with this? I mean, I never, ever, ever want to plot something like this. As if it is a function. The result of that is probably because it's this thing points in the same direction as that one. No, not really. It's still a loop like this. It's just going too far away. It's also a very interesting discontinuity. Oh, it's not discontinuous. ting, 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 ting. Why? It's just... I mean, why not draw something like this when it draws this? Because it's just not existing. You gotta wonder how that is working mathematically, that it does something like this. Almost not moving it. Pretty fast. So in 3 steps we are there. Okay, I think I'm gonna take a break. I'll fix what is in the description of the video. I wonder if we can somehow detect that this loop exists. I think it's just a red flag that the length from P1 to the control point here and from here to there is longer than the distance from P0 to P1. You don't want that. Then you get this kind of excesses. Wait toward until that is no longer the case. I even have to go further because see, this is still longer, I think, than this. Say more or less here. It's maybe no longer the case. Now you can argue that this is a reasonable curve. Hmm. Sure. Look, it's going through P1 twice. So this feels so three-dimensional. I bet you can look at this as a projection of something three-dimensional that will look way better than this. This kink here is absolutely horrible. I mean, why the fuck? But if you imagine that this is just a nice smooth curve that is here just changing in the z direction, and then like this, and then here it's going up in the z direction. It's probably something smooth. See, and then it just nothing much happens really. It just rotates over itself in this direction. But I think we're just looking at the wrong way at this curve. You should use a one higher dimension. This discontinuity, or at least it looks like a discontinuity, it probably isn't. Just these super fast jumps. Oh, well, actually it is a discontinuity. Yeah, the direction here changes. So that's exactly when the... Let me see where I printed. It's the y coordinate of alpha. Becomes negative. So this becomes negative. Excusez-moi. Do you know the thing is positive? And if I move it a tiny little bit, it's negative. And now, because it makes such an enormous detour, at the same time the G value is changing, I think, because this is super large. So it's making an enormous detour, and then only at the end, when it almost reaches the 1 value, it passes through P gamma. If I change this a tiny little bit. Oh. Well, that's surprising. It's still 0.83. Yeah, should stop wasting time, I guess. Yep, totally works. Totally works. Could draw a vertical line here through the zero that we find, but the last step was a thousandth of this, so it's totally going to more precisely than 1 pixel through the zero here. I guess on the other hand, it doesn't really make sense. Oh, needs a lot of steps. Still not using a bracket method, just even once here. Yeah, hello Wolf. Okay, I'm gonna stop for now. Let's play a game of chess or something, and then go for a walk, and then eat something. Hmm. Starting to regret that I did not castle. Oh shit. Stupidity. I think I was pretty bad already anyway. Yeah. Not really. 0.3 for white. Yeah, that would be better. You can still... I just want to just stop the pawns from advancing. Then putting rook here is even better. You cannot advance this one, take it, and cannot advance this one because I take it. If I put it there, he could still... Well, he has to defend that one then, but he wants to go behind it anyway. Draw his position. And he plays this anyway, wow. More likely, he would chase my knight away. I would go back and then put the rook behind it. Yeah, no need to defend this square, I guess. between here or there. I think this is better. You can push the pawn, maybe still defending the knight. Block the pawns. Yeah, okay. I don't know. So, oh, he doesn't have to take it. Yeah, this one. Stupidity. The hook here. No. Hook here, maybe. Okay. Can't lose this pawn, right? And then this thing just walks. It's gonna cost me a bishop. I don't have much here on this side. That would be the best one, but the king is even still in the square. It's not going to be... Nah, you can never lose this one. So... could take the knight, and then the bishop. So if he takes my... yeah, if he takes back, then I win a bishop. So if I take the knight, he has to take my bishop. Then I can take this pawn. Then we have opposite colored bishops, but maybe I still win then. Alternatively, now we have a problem, of course. I mean, this is a backwards pawn. So I take here, I take with check, you go there, it goes not there, because my bishop is here. I have to defend this one. Okay, the knight must go back in that case. And then, yes, I could take it. And then I can maybe collect this pawn. So we go here. King here, king here, king there. King here, king there, king here. I can collect this pawn. Might win as well. Which is better, take the knight or take the bishop? I win this pawn afterwards, I think. Or not. So it takes here, I take this pawn. Bishop goes here maybe, king goes here. Pawn goes up. No, nothing. Just one move too late. Yeah, it's this one. I can just take this one or that one. It's still not over though. It wants me to decide. Probably this one. Go here. No, actually. Which pawn to take? Take this pawn and I can go here. And I threaten to take this pawn. defending that. But I could push it. Tick, tick. And this one is still weak. How the hell can this not win if I take the wrong pawn? It looks like both should win. I'm gonna go for this one. Hey! No. Why? 50% chance. That must be that pawn then. Yep. And that is finished. Yeah. Had a 50% chance there. So no idea why. This is the only winning move because drum ruffle. Yeah. It's not working anymore. I'll leave something related to the project as a thumbnail. Okay, I'll be back later today, I think.